Hi, I'm Hlér Kristjánsson, and I'm going to tell you a bit about our work on resource theories of communication. In classical physics, communication is described in the framework of Shannon theory, where classical particles transmit information through fixed communication channels. Quantum Shannon theory generalizes this to the quantum case, where the information can be encoded in the state of a quantum particle. In a series of recent works, a further generalization of quantum Shannon theory has been proposed, where also the configuration of the communication channels is described by a quantum state. Researchers have considered new ways of combining communication channels in a quantum superposition of alternative configurations. For example, two channels can be used in alternative to one another, and the choice of which channel is used can be in a quantum superposition. This is achieved by letting the information carrier travel on a coherent superposition of two trajectories, passing either through one channel or through the other. Another example of a quantum configuration is the superposition of causal orders. Two channels, A and B, can be combined in two alternative orders, AB and BA, but also in a quantum superposition of these orders, giving rise to a new primitive known as the quantum switch. These new ways of combining quantum channels have been shown to provide various communication advantages, such as the enhancement of different types of channel capacities. However, the quantification of these advantages and their comparisons has been the subject of considerable debate. An important reason for this debate was the lack of a well-defined framework within which the different extensions to quantum Shannon theory could be formulated on an equal footing. In this work, we formulate a general framework for communication as resource theories, which enables a formal quantification of the different ways of combining communication channels. Our framework takes communication channels as the initial resources, and describes the different ways in which these resources can be manipulated. The initial resources are unplaced quantum channels, that is, channels that have not yet been placed between the communicating parties. Now, these can be transformed into placed channels, that is, quantum channels whose input and output are placed at the location of the sender and the receiver. The operations on the initial resources are transformations of quantum channels, which are called supermaps. These come in two types. First, we have transformations from unplaced channels to placed channels, which we call placement supermaps. Examples of placement supermaps are the parallel placement and the sequential placement of standard Shannon theory, as well as the superposition placement and the switch placement considered in recent extensions to quantum Shannon theory. Secondly, we have transformations on the placed channels, which we call party supermaps, corresponding to local actions of the communication parties themselves. A choice of allowed supermaps defines a resource theory of communication. However, not all choices are sensible. For example, one should not include supermaps which simply throw away the initial communication channels and replace them with a perfect noiseless channel. Allowing such supermaps would render any theory of communication completely trivial. Therefore, we propose a minimal requirement which we call no side channel generation, namely that no allowed operation should enable communication independently of the initial communication channels. In other words, it should not be possible to construct a communication protocol that works independently of the communication resources initially available to the sender and receiver. With our general framework in place, we discuss how the communication advantages arising from different choices of free supermaps should be interpreted, and comment on the comparisons that have been made across different communication models. We hope that this work will be useful in constructing new quantum communication protocols and in assessing their performance.